Hello everyone, my name is Andres Nemetsky. I work under Dr. Story with Garrett Campbell here, and the focus of our research was to try to synthesize this molecule via Friedel-Crafts addition in a model study in hopes of using this chemistry to functionalize a dehydrogenated PIB-Styrene copolymer. What is PIB? PIB stands for polyisobutylene, and it's a polymer of isobutylene, shown here. And I'm going to pass around a sample of polyisobutylene that my grad student Garrett synthesized in the lab, so you can take a look at it. Turn it upside down. So polyisobutylene is a synthetic elastic polymer, and it's extensively used in the adhesives and sealants industry. It has such properties such as having a low glass transition temperature, which is the temperature at which it transforms from a rubber into a glass, and this happens at -62°C. This gives PIB good flexibility at room temperature, and also high adhesion and permanent tack. It also has no electrical conductivity, so it's used as an insulator with some applications involving wires. It's also non-toxic and bioinert, which gives it medical applications such as being used in surgical tape adhesives and transdermal systems or transdermal patches like the one shown here. I know there is research being done right now where PIB is being used to deliver the opioid drug fentanyl, and that drug is active in the microgram range, and PIB's permeability properties allow it to do that. PIB also has low permeability to moisture, air, and gas, which makes it a good sealant. And it is also used as an additive to enhance adhesive toughness. What is toughness? Toughness is the area under the stress-strain curve. Here we see a blue line where it represents an adhesive where PIB has not been added, and the red cross here represents the rupture point. So once PIB has been added, you'll see that the area under the curve increases as its toughness increases. So the material is able to elongate more, but it can handle less load. You see it's lower on the stress. PIB is also chemically stable. Why? Because it has no unsaturations in the backbone or methine hydrogens, which makes it also less susceptible to UV oxidation, and it also has limited reactivity due to the sterically hindering methyl groups. Some industrial products that use PIB adhesives are ExxonMobil's Vistanex and BASF's Openol. One can custom tailor how one's PIB performs based on the molecular weight or degree of polymerization shown here. So if you wanted a polymer which was a good adhesive, you would pick something in around the 50,000 range. You would see it has good barrier properties, good tack, good adhesion, and low viscosity, no elasticity. So as a review, for a higher molecular weight, you have a stronger polymer and it's more elastic, and for lower molecular weight, it's more soft and liquid-like. And in an industrial setting, this is controlled with temperature. What you'll see here in the picture here is a dental composite, which PIB is currently not being used for, but that brings us to our next slide, which is catechol adhesives. What is catechol? Catechol is its functionality shown here on the chain, and it is used in nature by mussels which secrete block copolymer proteins that can display rather remarkable feats of strength, such as what you see here, a mussel holding up a brick. And this is what the functionality looks like in a mussel. Synthetic applications of catechol include orthopedic cements, dental composites, surgical glues, and even fake nails and eyelashes. A study was performed by Wilker and Perez, which investigated catechols' adhesive properties compared to other well-known glues, such as Elmer's white glue or polyvinyl acetate, and crazy glue or ethyl cyanoacrylate. And they found that at best, this polymer was comparable in its performance. You see here in the strength column, it's 7 plus or minus megapascals, which is comparable to crazy and Elmer's glue, but not as good as epoxy. How did they test this? They used lab shear adhesion testing, which you'll see here in the diagram. You have two surfaces pulling apart at each other, And this pressure here is calculated by dividing the point at which it ruptures, the force at which it ruptures, divided by the contact area with the pressure. What variables did they test? They tested the ratio of catechol here to styrene to see what would result in the best adhesive. Why did they choose styrene? Simply because styrene is most similar to catechol. What did they find? You'll see in the red curve here, where the x-axis is catechol concentration and the y-axis is adhesion, that the best adhesion was demonstrated at around 33%, which you see right here, of catechol to styrene. What is this blue line? They cross-linked the polymer here with pyridate to give it a much higher performance, which results in this number found here. I believe muscles don't use pyridate, but they use iron as the cross-linker. So why do we care about all this? Because we hope to make an even better adhesive, which is catechol functionalized and has a PIB backbone, to take advantage of PIB's already adhesive and tacky properties and catechols' adhesive properties. So how we originally planned to do this was to start with methyl benzoate and to perform a Grignard reaction and then a subsequent dehydration. However, this did not work for us, so we followed a different procedure, starting from 3,3-methyl butyric acid and performing a self-condensation reaction with trifluoric acetic anhydride catalyzed by triplet acid, and then refluxed it, this is the hydrolysis step here, and then refluxed it under acidic conditions to make this ketone. This, for us, was successful. Now what we plan to do is to react this with a phenolithium and then dehydrate it to form the compound that we originally saw. You see here, it's the same thing. Then what we'll do is, what is the focus of our study is the Friedel-Crafts addition with this phenoxy compound under the presence of Tickle catalyst at negative 70 degrees to form this compound right here. And at this point I wanted to mention that this is a model study and that eventually this is what we hope to accomplish. Although this is not exactly the focus of our study. The focus of our study is rather to make this compound, to study this chemistry. So how we do this is we start with the PIB-Styrene copolymer and perform radical dehydrogenation to get this unsaturation here, and then perform the same chemistry here with the phenoxy group and Tickle catalyst to form this compound here. And then at this point we will react it with dopamine via multi-step procedure to make this final catechol functionalized PIB polymer. So in conclusion, we hope to make a much better adhesive which takes advantage of catechols' adhesive properties and PIB's tacky and adhesive properties. Any questions?